Most people get this question wrong. It is actually a reasonably straightforward rotation question, yet you will find that most people get this wrong. Let's look at the question. So here I have a rod, it's a uniform rod of mass 2.4 kg that has basically been pivoted at one end. There is a frictionless pivot, so you don't have to worry about friction due to the pivot. It is released when it is in horizontal position and it is released from rest. That position I am calling it 1. So when you release it, what is going to happen? This fellow is going to come down, right? So as it comes down here, when it makes an angle theta 60 degrees, that is at position 2, the question asks us to find the force that is exerted by the pivot. See, I have to hold this rod. So the pivot will have to hold the rod, right? So if I leave it, it's not like I've just left it, released it. So the pivot has to hold the rod. So when it comes to this point, what is the magnitude of the force exerted by the pivot on the rod? You know, moment of inertia of a rod is ml square by 3 when you are basically talking about an axis passing through. The axis is horizontal like that. The axis, when it's passing through this point, one end, you know it is ml square by 3, that you already know. So here you're talking about torques. So look at torque, look at I, moment of inertia, and use that to find out what is the force exerted by the pivot on the rod. Try it out. Once you've got it, look at the solution. Let us first look at the most common wrong answers. Many people write the answer, the force exerted by the pivot is mg, which is 24. This is wrong. Mg cos theta is the next most common answer, which is also wrong. Mg cos theta by 4, people have done a lot of work to get this answer. That is also wrong, and some of you may be surprised why. So 3 newtons is not correct. Mg sin theta 20.78 is also not correct. The correct answer turns out to be mg by 4 into root of 1 plus 99 sine square theta, which is 52.05 newtons. Let us exactly see how we can get this answer. So if you see this rod has its center of mass, because it's a uniform rod, the center of mass is right in the middle, right? So let us assume the rod has length L. So then I can write this is L by 2 and that is also L by 2. mg is going to act right in the middle, acts at the center of mass downwards. And when the rod comes to this position also, the center of mass is right in the middle, and therefore you're going to get mg acting this way, downwards. Please remember it is acting downwards. I'm going to use two equations. I'm going to use tau is equal to I alpha about the pivot. So about the pivot, let's call this pivot P. So torque about the pivot is I about the pivot times alpha angular acceleration. The second equation we are going to use is net external force on this entire rod. So that will include mg, it will also include forces acting at the pivot. Okay, that must be equal to mass of the rod into acceleration of the center of mass of the rod. This is the center of mass. Okay, let me write this center of mass here. So I hope that is clear. So we are going to use these two equations. I hope you know these two equations. And it's very simple here because I about the pivot is also quite straightforward. I about the pivot is ml square by 3, because this is just, we are talking about an axis perpendicular to the rod passing through one end. So these things are things that you probably already know. The only question is when it is here, what is the torque? Well, torque about P due to the force acting at the pivot is not required, because you see the forces acting at the pivot, maybe they are acting in this direction, some weird direction like that F, right? So now that force passing through the pivot, what is its torque? 0. So the only torque that I need to worry about is mg. But you cannot say mg into L by 2. You can't write mg into L by 2. That's not the torque, because at this position you can say mg into L by 2. At this point mg is this way, L by 2 is like that. So clearly mg into L by 2 is not the torque. Okay. Then what is the torque? To find the torque, we need to resolve mg into these two directions. We can also take the perpendicular distance, but I like to resolve it like this because it will turn out to be useful in the next step. So if you see this angle is theta, which means if I draw a line here, this angle would be theta, this angle would be 90 minus theta, this angle would be theta. So this angle is theta. Okay, you can check that out. This is, these two are like making an angle theta, and when it turns and becomes perpendicular, the perpendicular to the rod will also turn by the same angle. So therefore this angle is theta. So this is mg, this is going to be mg cos theta. So this is mg cos theta, and this force here is mg sin theta. I will do the whole thing in terms of theta. Last step we will try and substitute. I don't need to worry about mg now because I have already resolved. The torque is entirely due to mg cos theta, because mg sin theta is a force that is pulling along the rod. So what is the torque due to that about point P? 0, because it's right like this. So it actually passes through point P, therefore you don't have to worry about the torque there, right? So what we have done is to resolve mg into mg cos theta and mg sin theta, and we are only interested in this right now. So torque about P is mg cos theta into L by 2, mg cos theta into L by 2. That's clear? So this torque, which is trying to turn it this way, must be equal to I alpha. I already know I is ml square by 3. So ml square by 3 times alpha. So if I now look at what is alpha, we can solve for alpha. So if I cancel out m, l, m, l, you can take the 3 up there. So 3g by 2l cos theta. So this is alpha. That is the angular acceleration, right? So this is alpha with which the rod is accelerating, angular acceleration at this instant. Now you can notice something interesting. If I took this rod and I left it when it came to this point, at this point it may have a large speed, but at this point its acceleration should be 0. Angular acceleration should be 0. Is it 0? Well, theta becomes 90, cos theta becomes 0, so it does become 0. So it's a good solution. And if you take this point, then at that point theta is 0, so that should give you the maximum angular acceleration. Cos theta is 1, so you will get 3g by 2l at that instant. So that's fine. So we've got alpha, but that is not the question. The question is find the force exerted by the pivot on the rod. So let us think about that again. Why would there be a force exerted by the pivot? What should I use? I should use external force. Net external force must be mass into acceleration of the center of mass. What is the acceleration of the center of mass? Now this is where what most people do. So they write acceleration of the center of mass is equal to alpha times r alpha. So we are going to use the formula r alpha, and then we get L by 2 times alpha, and if I substitute L by 2 times alpha, so you put the L alpha there and divide by 2, you will end up with 3 by 4 g cos theta. 3g by 4 cos theta. Correct? All I have done is to say L alpha by 2. So once that goes there, 3g by 4 cos theta. Unfortunately, this is not right. Well, what would have happened if this was right? Well, if this was right, then what people do, so I'll just show you what people will do right now, and then we will come back to why that is not correct. Because if I started off with this and I say, oh, here is F, so let us take force in that direction, component of the force in that direction. I will call this F perpendicular to the rod. Then you can start off by writing mg cos theta minus F perpendicular, which is that, right? Mg cos theta minus F perpendicular. What is that equal to? That must be mass into acceleration of the rod. So if I use mass into acceleration of the rod, and this I use as acceleration, so I'll write 3g by 4 cos theta, and then you get F perpendicular. If I take it to that side, you will end up with mg cos theta by 4. Now, if you have got this far, you are doing well, except you have forgotten a very important point. So this is the kind of mistake that many good students who have actually understood the concept and reached this far, you have really understood quite a bit, because you have understood how to calculate alpha correctly. You have also understood how to calculate acceleration with some small error there, and then you have also figured out how to use it to find out what the force is. But then why is this wrong? Why am I saying this is wrong? Because if I had given you the same question and I told you that I had left this rod in this position. It was released not from position 1, but it was released at position 2, then this would have been the correct answer. Because you calculated alpha, you calculated this, you calculated that, everything would have been fine. So what is the big difference when I am releasing it there versus releasing it here? What happens if I release it there? By the time it comes here, it already has an omega. On the other hand, if I released it here, it has 0 angular velocity. It was released from rest. Okay, so what is the big deal? So what if it was released from here or released from there? How does it make a difference? Let's see. If it was released from here, right, you don't have to worry about this. You will still have one more component, which is this component. How much is that? That is going to be something I'll call F parallel. If it was released from rest here, then F parallel will have to be equal to mg sin theta. So if I now substitute theta is 60 degrees, then this would basically become mg by 8. Okay, and m was 2.4, so 24 by 8 is 3. So this will become 3, and this here will be mg, which is how much? 24, because m is 2.4, g is 10, into sin theta, which is root 3 by 2. So this is 12 root 3. And so if I did root of, because you see this force and that force, so you are looking at the magnitude of the force. So if I wrote root of 3 square, which is 9, plus 12 root 3 square, 12 square is 144, 144 into 3. This will give me root of 441, which is 21 newtons, right? Now this is also a very popular wrong answer. Now this person has done a lot of work, has not just found the perpendicular component of the force, has also found the force along the rod. They have done everything, but then why is it wrong? So now let us look at what exactly is the mistake, then we will try to solve it. By the time it comes here, this rod has a velocity because it was released from here. And so what if it has a velocity? Well, if it has a velocity, it is moving in a circle, there will be a centripetal acceleration. There will be a centripetal acceleration. V square by r or r omega square. There is an omega, so you need to worry about r omega square. In this case, r is L by 2. So this is not the entire acceleration. This is only a component of the acceleration. This is the tangential acceleration. So when the rod moves, A equals r alpha doesn't give you the full acceleration, it gives you the tangential acceleration. So there is also a r omega square, which is the centripetal acceleration. You already know it, but often people forget it. So now let us include that and do the calculation. The fact that we have included that does not mean this is wrong. So this part still remains as it is. This part is wrong. This answer 21 is also wrong. So let us now find out what is the correct answer. So centripetal acceleration is going to be r omega square, for which I need to find omega square, but r in this case is L by 2. So this is L by 2 omega square. Okay. So mass of the entire rod concentrated at the center of mass. So center of mass, it's moving this way, accelerating. Therefore the acceleration is that way. So it's going in a circle like this, acceleration is that way. Okay. So I need to find L by 2 omega square. How will I find omega square? How will I find omega? Well, use energy, because it's a frictionless pivot, so there was no loss of energy. So if I drop it here, by the time it comes here, it has converted potential energy into kinetic energy. So how much is the loss of potential energy? That is the question, right? So what was the drop in height? That is the question, because if this is my center of mass, the drop in height is this height. So this is how much it has dropped in height. L by 2 cos theta will be this component. L by 2 sin theta will be the drop in height. So therefore, the potential energy drop is m into g into the height that it has dropped by, which is L by 2 sin theta. L by 2 sin theta. But the loss of potential energy must have become gain in kinetic energy. What is the formula for kinetic energy for a rotating rod or for any rotating object? Half I omega square. So let me write that down. Half I already know is ml square by 3. So it is ml square by 3 into omega square. Notice I don't really need omega, I need L omega square by 2. So we can try to cancel things out. So let me first cancel an M here. Let us cancel this L there. Okay, there is L omega square by 2 sitting there, right? Which is what I want. So all I need to do is to take this 3 to this side. So you know that this AC, which is L omega square by 2, L omega square by 2, if I take this 3 to this side, you will be able to see that it is going to be 3g by 2 sine theta. So usually you should try, when you solve problems, you should try to do this. Don't try to find omega, square it, take the square root, too much work. Okay, so I've got acceleration centripetal. Please remember, this is center of mass, acceleration tangential, this is acceleration centripetal. Okay, that is in this direction. Again, I have to write this. F external is mass into acceleration. Now I wrote that F external is mass into acceleration along this direction. Now I have to write it along that direction. Along this direction it was not a problem because this was one force, that was another force, right? They were both perpendicular to the rod and the acceleration we had taken as being perpendicular to the rod, so it was quite straightforward and simple. Now what I have to do is to take the same thing along this. So let us write that equation down, and what is the equation? It is directed this way. So mass into acceleration, mass into AC, which is 3 mg by 2 sine theta, because this is 3g sine theta by 2, so into m. So what have I written? Mass into acceleration in this direction must be F parallel minus mg sine theta. What about mg cos theta? Oh, that is perpendicular. Perpendicular does not matter. For this direction, only these two forces matter. So I will write F parallel, parallel means parallel to the rod, minus mg sine theta. Well, if you combine these, you will find F parallel, take it to that side, 1 plus 3 by 2, because this is also mg sine theta, that's also mg sine theta. So that is how much? 5 by 2 mg sine theta. So I have now found the parallel component of the force and we have found the perpendicular component of the force, so we need to combine, because F magnitude is root of F perpendicular square plus F parallel square. That's all. So let us combine this and this together. You can see that the mg is common. So in fact, let me rewrite it for convenience as 10 mg by 4 sine theta. You will see in a minute why that is the case, because you see that mg by 4 is common. So when I try to combine it together, I can write F is equal to root of mg by 4 will come back together. So mg by 4 square, mg by 4 square cos square theta plus 10 sine theta square, which is 100 sine square theta. Correct? So this is equal to mg by 4 root of, now one cos square and one of the sine square you can combine and make it 1 plus 99 sine square theta. So this is the answer to the question, right? Let us now substitute the values that we have. So if I substitute the values, you find mg, m is 2.4, g is 10. So 2.4 into 10, 24. So 24 by 4 is 6. And then here we have root of 1 plus 99 into sine square theta. Sine theta, this is 60 degrees. So sine theta is of course root 3 by 2. So root 3 by 2 square is 3 by 4. So that is going to give me 297 plus 4, 301. And so this will come out, it will become 2. So you will get 3 times root of 301 newtons if you want to be exact. But of course we want an approximate answer, so which will be 52.049 something. So it's 52.05 newtons. So the closest integer answer would be 52 newtons. So the answer to this question is 52 newtons and not the other answers that you got, 21, 3 and so on. Please remember, this is a very tricky question in that sense. It is a simple question, it's not very complicated. You can use energy to find out the omega, and it's just tau equals I alpha, that's it pretty much. So tau equals I alpha, net force External force is mass into acceleration along the rod, perpendicular to the rod. Simple. The problem is, perpendicular to the rod, R alpha is something common, people will use it. Parallel to the rod, they forget, because if you look at this entire question, from here to there, there was an energy transformation from potential energy to kinetic energy that produced an omega, and once you have an omega, you also have to worry about centripetal acceleration. Therefore, this force is not equal to mg sin theta. So, you will have to basically take into account some of these details. So, I hope you understood what to do in a question like this. It's a little bit of a tricky question, but at principle level, it's a very straightforward and simple question.